All right, everyone. Hello and welcome to the first pre-recorded tutorial. We're going to start where we left off with question 2.4. So, okay, we have a stainless steel cooking pan without a lid with an inner diameter. During boiling, the water level drops by 8 centimeters in 40 minutes. And the question is, what is the rate of heat transfer to the cooking pan? So we're boiling something, we're losing some amount of water per unit time because it's being converted into steam. Now, when something's being converted into steam, what's happening? We're adding enough energy to take it all the way enthalpy-wise from HF to HG. Okay? And again, enthalpy is always in terms of kilojoules per kilogram. So if we can identify the state that this is in, then we can find HFG. And if we can identify the amount of mass that's leaving in 40 minutes, we can see how much energy in those 40 minutes we're putting in to make that amount of mass leave and become vapor. And then all we have to do, because they want a rate of heat transfer, is we have to divide it by those 40 minutes to get the actual rate of heat transfer. So let's go ahead and do that. There we go. I'm just going to open up the question on a different screen. And okay, so, all right, so we have, let's start by finding the mass of the water, okay? Now we know mass is equal to the volume, which I'll denote with a little strike through, divided by the specific volume, right? That's how we can find the mass. Now, what's the volume? Well, it's basically the volume of a cylinder, right? The amount of water that leaves. If it's a circular pan and we lose a height of 8 centimeters, we can treat it like a cylinder. It is a cylinder. And of course, the volume of that would be pi over 4d squared. Now, diameter of the pan is 22 centimeters. And we're multiplying it as well by the height. Pi over 4d squared is just the base, and now times the height of 8 centimeters. This is the volume that we lost in those 40 minutes. Now we also have to find the specific volume, okay? So remember, specific volume is like the opposite, or the inverse, more accurately, of density. And we can get that from the water tables, from the property tables. But to use the property tables, we have to know what we're looking for. And what are we looking for? Well, we're told that the pan is open to the atmosphere, right? And that means something. That means that we're working with atmospheric pressure. And since we're working with atmospheric pressure, we know that water and atmospheric pressure boils at 100 degrees Celsius. So we know we're working initially with a saturated liquid at 100 degrees Celsius. So let's go and look for that in the property table. So this is sorting by pressure. We want to go by temperature here. So checking, this is indeed the water table, not the refrigerant one. We have temperature at 100, okay? And we see that VF, being the saturated liquid, the saturated liquid's specific volume, is 0.001044 meters cubed per kilogram, right? So good, that's what we're looking for. So let's go put that in here into our little equation, 0.04. And if we calculate all this, we're going to get the mass of water that left in those 40 minutes. And we can see by calculating this that would be 2.91 kilograms. So we've lost in 40 minutes 2.91 kilograms as vapor. That means in 40 minutes we've given enough energy to vaporize 2.91 kilograms of water. But how much energy is that? Well, again, if we go back to the water table and we look, here we go. If we look in the enthalpy area here, we see we have the enthalpy as a saturated liquid, the enthalpy as a saturated vapor, and in between we have this, which is the difference between the two. And that's really how much energy we're putting in to go from one to the other, right? And if we go to the 100th row, we find that the energy that it costs to go from a saturated liquid to a saturated vapor per kilogram is 2257 kilojoules. So coming back here, we have per kilogram is 2257. So it costs us 2257 kilojoules per kilogram. But we're multiplying this guy by 2.91 kilograms, because if it's this much per kilogram, then how much is it for 2.91 kilograms? And the answer is 6567.87 kilojoules. 6567.87 kilojoules. Now, this is how much energy it takes to boil 2.91 kilograms of water at the state that we're given. But they don't want to know the amount of energy. They want to know the rate of energy transfer, right? Now, luckily, they tell us that this all happens in the course of 40 minutes. So all we have to do is divide this amount of energy by 40 minutes times 60 seconds, of course. And if you do that, you should get a rate of heat transfer. And since it's kilojoules per second and not just joules per second, our answer is going to be in kilowatts. Now, if you calculate that, you should get 2.74 kilowatts. So that means every second we're giving 2,740 joules to this system, okay? Now, lucky for us, there's part B. Let's go have a look at part B. And it is, starting from this part, what would be the boiling point? What would be the boiling temperature and the water level after 40 minutes while keeping the electric power input if a heavy lid is used initially to double the pressure inside the cooking pan? Okay, it's a long sentence, so let's unpack that a bit. So first of all, now we have a lid. Before we didn't have a lid, right? And you remember earlier on we talked about, because there's no lid, we know it's atmospheric pressure, so we know the boiling temperature. But since there's a lid and they tell us that this lid is going to double the pressure inside the cooking pan, well, what's atmospheric pressure? It's about 100 kilopascals. Okay, so times 2 is 200 kilopascals, or 0.2 megapascals, okay? So we already know kind of where we're looking in the water tables, okay? We're looking at the line for 0.2 megapascals. So what would the boiling temperature be? Well, it's as simple as we just look in the water tables. It'll explicitly tell us, right? So, sorry, new to the whole iPad thing. There we go. Yes, water tables. Now, in this case, we don't really care so much about sorting by temperature, because that's what we're trying to find. What we want to do is sort by pressure. Now, we know it's double atmospheric pressure, so 2 times 0.1, so 0.2 megapascals. So I'm going to use this row here to determine my temperature. And I see that the temperature is 120.23. So what's the answer to the question? What's the temperature we're boiling at? 120.23 degrees Celsius. It's that simple. Okay, but that's not all they're asking. They are also asking, what is the water level after 40 minutes while keeping the electrical power input the same? Okay, so the electrical power input is what we found before, that 2.74 kilowatts. We're saying that hasn't changed. That's still the same thing. But remember, we're now at a different state because the pressure is different. We're now at a different state. So we have to now go and see what the exchange rate is, shall we say, in terms of the amount of energy it costs us to vaporize an entire kilogram, right? So at a different row in the table, our HFG is different, right? Before it was 2257, now it's going to be something else. So let's go back to the water tables and check what that would be. And we see that HFG is this one here. I think I'm off. No, that's it, 2201.9. Okay, so again, now before it was like something like 22, I don't remember, but we found HFG before for a different state, okay? Now we have a different pressure or at a different state. What's HFG in this state? How much energy does it take to vaporize 1 kilogram of water? Well, it takes 2201.9 kilojoules, okay? So let's just write that down. 2201.9 HFG equals 2201.9 kilojoules per kilogram, okay? And in 40 minutes, how much are we going to be able to vaporize? Well, we know it's the same power output. We know it's still 2.74 kilowatts. So 2.74 kilowatts, that's 2.74 kilojoules per second, okay? times 40 minutes. So 2.74 times 40 times 60. That means 65, 2.74, 40 times 60, 6567. That's just a bit of round off there. But the point is it should be the same energy input here because it's the same heat input for the same amount of time. So you don't even really need to calculate it. You can just use this value over here. So we know we're putting in 6567.87 kilojoules, right? But if we divide that by HFG, which is how much it costs in terms of kilojoules per kilogram to vaporize something, kilojoules per kilogram, we're going to be left with units of kilograms. And specifically, we're going to be left with how much water we've boiled off in these 40 minutes. And if we do the math, we should get a value of 2.98 kilograms of water, which is a little bit higher, a little bit greater, I should say, than what we had before, which is 2.91. But they don't want to know the mass we boil off. They want to know the displacement of the water level, right? So we just take this guy and we sort of reverse solve it in what we did before over here. And we're trying to solve for the actual height, okay? And it's just now algebra, you plug this guy instead of m, okay? Basically, we're going to multiply this guy by the specific volume, okay? So the specific volume we have to find again from the water tables for this new value. And we can do that from here. VF is 0.001061. So the, God, there we go. 0.001061, as I think I said. So, sorry, times. We want to multiply this guy times 0.001061, and this gives us the total volume. And that would be 3.16 times 10 to the negative 3. Meters cubed, right? And then just from the formula for the volume of a cylinder, we're going to go backwards and solve for this guy, for the height. So that means we're basically going to say the volume